Greetings from Hacettepe University, Turkey. It's Yahya Kerem, the team leader of Space Troopers Hacettepe Rover team. We are proud to introduce our third generation rover Mary. Space Troopers was established in 2019 with a vision to advance the future of the space technologies. Since our foundation, we have maintained a consistent growth trajectory in national and international competitions, such as European Rover Challenge, Anatolian Rover Challenge, Technofest, and also we attend various exhibitions. Our first achievement was in the remote category in 2023. We then participated in the on-site category in 2024.
The mechanical team consists of 4 members, responsible for the design, analysis and manufacturing of the physical form of the rover.
Electronics team with 10 dedicated members responsible for embedded software, PCB designs, internal communication process and power management.
Our team consists of 4 students who are majoring in computer science and electrical and electronics engineering. We focus on autonomous navigation of the rover and drone, communication systems and ground station applications for the ease of use.
Our team's main task is explore the habitat of Torbic and research for the traces of past life. We will collect the necessary concrete field data to test our astrobiology hypothesis.
The organization unit acts as the team's operational core. We manage the logistical and the promotional side of the project to ensure the technical units can stay focused on the rover's development. We organize events and represent the Space Troopers rover team on international and national platforms to increase our visibility in the space industry. The Space Troopers rover team consists of 25 members, divided into 5 main sub-teams: mechanical, electronics, software, science, and organization led by the team leader. We combine different engineering backgrounds to achieve a common goal. Today, we are actively competing in the European Rover Challenge. Our team operates at Hacettepe University's Beytepe campus, utilizing the facilities of the Hacettepe University and the Electrical and Electronics Engineering Department to develop our rover.
We are participating in the European Rover Challenge to gain first-hand experience of the international standards and to prove out the team's engineering capabilities on the global stage. We aim to transform the theoretical knowledge of our team members from diverse disciplines into practical and innovation solutions specifically for planetary exploration vehicles, and to create an international collective structure with fellow students who share similar ideals and strive towards the same goals.
The foundation of our rover is a high-strength chassis engineered from aluminum T-slot profiles and precision laser cut brackets. This architecture prioritizes modularity, allowing us to rapidly reconfigure the platform to meet the specific demands of diverse mission profiles. For superior mobility, we have integrated a rocker buggy suspension mechanism. This ensures constant wheel contact and optimal traction across the most challenging terrains. We aim to integrate a 4-wheel steering mechanism into the rover to maximize operational agility. However, the physical fabrication of this system remains incomplete. Our wheels are hybrid construction. FTM manufactured ABS rims paired with high-grip TPU tires, balancing structural rigidity with impact absorption.
In its fully assembled form, the system weighs around 70 kilograms, with an operational footprint of 120 cm in length, 108 cm in width, and 140 cm in height.
Our power system consists 2 discrete batteries, 10S lithium-ion battery and 4S lithium iron phosphate battery. This battery architecture and custom-designed power distribution board allows us full control over the power system. Power distribution board designed for handling vital missions such as different voltage levels, MPPT algorithms, and solar backup system. For emergency cases, every component protected with blade fuses and reverse current protection circuits. Additionally, kill switch and indicator light placed visible, rigid, and easily accessible location on rover. Our rover contains STM32 series microcontrollers communicating with main computer Jetson Nano and robotic arm computer Jetson Nano via UART communication protocol. For drive system, 4 encoder-equipped DC motors and custom motor drivers used. With STM32G series microcontroller and PID algorithm, we achieve precise movement.
The communication on the rover is established using 2 omnidirectional antennas configured in bridge mode. Both antennas operate at 5 GHz frequency band and use IEEE 802.11 communication protocol. To simplify operation and improve mission efficiency, a dedicated ground station application has been developed to easily monitor and control all platforms. A fail-safe protocol is implemented to ensure safety in case of communication loss. The rover stops all movements if the data transmission is interrupted. ROS2 is utilized as the primary software framework of the rover, providing modular communication and coordination between all onboard and ground station subsystems. Our system is built around 2 onboard computers, each dedicated to different tasks. Two separate onboard computers are utilized to increase computational capacity and to isolate critical subsystems. This distributed architecture improves system reliability by ensuring that in the event of a failure in one subsystem, the remaining system can continue operating independently. For localization, we combine wheel odometry with a LiDAR inertial SLAM algorithm to achieve accurate and reliable positioning of the rover. The surrounding environment is mapped as a 3D point cloud by using elevation mapping algorithm. This data is then transformed into a 2D grid map, where each cell stores the corresponding terrain height information. Once the grid map is generated, the traversability of each cell is analyzed based on terrain characteristics such as slope, surface roughness, and step height. Using this traversability layer, the safest and most efficient route is planned through the Nav2 framework, allowing the rover to autonomously navigate challenging terrain.
The UAV system utilizes Pixhawk autonomous flight controller running Autopilot firmware for reliability and in-flight adjustments. For propulsion system, used brushless motors controlled by high efficiency and low latency ESCs. 3S LiPo battery used for providing power, while an onboard power module both regulates and monitors voltage for flight controller. For safety, remote controller includes an emergency stop switch, allowing immediate motor shutdown in critical cases. This configuration allows us precise and robust control under variable conditions.
For the droning subtask, our drone is designed to complete the mission autonomously, from takeoff to precision landing. The drone takes off from the ARCO ID 101 marker and detects the ARCO ID 102 landing target with its onboard camera. Then it aligns itself with the target and performs an autonomous landing. We use MATLAB and Simulink for image processing, mission logic, simulation, tuning and testing the full autonomous sequence before real flight. This helps us achieve reliable and repeatable performance for the 3 mission runs. ROS2 connects the drone onboard computer and ground station, transferring telemetry, video feed, mission status and control commands. The system also includes key safety features such as real-time monitoring, manual takeover, autonomous landing and fail-safe behavior.
Our primary manipulator is a 5 degrees of freedom robotic arm. Like the chassis, it utilizes a lightweight yet durable blend of laser-cut aluminum and T-slot structural members. Weighing it approximately 13 kilograms, it delivers an expansive operational footprint with a maximum reach of 1 meter. Actuation is driven by Manipulator stepper motors paired with planetary gear reducers, providing the high torque-to-weight ratio required for precise articulation. To maximize efficiency, we have implemented a differential wrist mechanism. This compact design significantly enhances our operational capability in confined spaces.
We implemented an inverse kinematics algorithm that enables easier and more efficient control of the robotic arm. The algorithm transforms input commands into precise joint movements, allowing accurate and direct control of the system. It also ensures smooth and stable motion of the manipulator, improving overall precision during tasks such as turning switches on or off, pressing buttons, and picking up rocks.
The rover's analytical heart is the science module, a high-precision suite designed for the autonomous collection and validation of geological samples. Our custom drilling mechanism is engineered to penetrate the subsurface to a minimum depth of 300 mm, ensuring we retrieve pristine material weighing at least 100 grams. To ensure structural stability during excavation, the drill utilizes a 2 degree of freedom system driven by a ball screw and a sigma profiles, providing smooth and rigid vertical movement in high-resistance soils. Once extracted, an auger functioning as an Archimedean screw transports the soil through a sealed plexiglass tube, a design that prevents sample leakage and cross-contamination. Finally, the sample enters a collection container, equipped with a high-precision weight sensor, providing real-time telemetry of the sample mass before safe transport back to base.
For drill and science system, used sensors and motors controlled by STM32 F-series microcontroller and communicating with main computer via UART protocol.
Our mission at Hacettepe Crater is based on a fundamental astrobiological principle. Polyhydraulic activity is an indicator of past life. However, because intense surface radiation and oxidation on Mars degrade organic structures, regolith analysis alone is insufficient. To access preserved biosignatures and present stratigraphic data, we drill to depth of at least 30 centimeters. By analyzing the sediments within these radiation-shielded subsurface layers, we model the region's habitability potential. Every in-situ analysis and depth sampling operating we perform aims to bypass these oxidized layers to find concrete evidence of life.
Robotic arm system has step motors, DC motors and servo motors, all controlled by closed-loop motor drivers. STM32 F-series microcontroller and robotic arm computer allows us precise and smooth movement.
The end effector is equipped with a two-fingered adaptive gripper. Featuring flexible high-friction fingers, it is designed to securely conform to a wide variety of object geometries.